Hi friends, today we are going to discuss the partial ordering of sets, relations. So any binary relation R in a set P is called partial order relation if P satisfies all the properties of equivalence relation. What are the properties of equivalence relation? So reflexive, transitive, as well as there we discuss the symmetric. Here it is antisymmetric. So reflexive, antisymmetric, as well as transitive. If the relation satisfies all these three conditions, then the order pair is known as partial order relation. Then the order pair is known as partial order relation. What do you mean by reflexive? So already we discussed in the second video that A of A relation A, for all A belongs to set, then it is reflexive. Similarly, what is antisymmetric? So A relation B and B relation A, then A is equals to B is known as antisymmetric. So transitive, what is transitive? If A relation B and B relation C, then automatically A relation C is also belongs to the that relations. Then we say that relation is transitive relation. That relation is transitive relation. So any relation on a set, if it satisfies all these three conditions, then we say the relation is partial order relation, and it is denoted by this symbol P, this symbol P less than or equals. So it is different from less than or equals. So order pair, this P of less than or equals, this one is called poset. Partial ordering is also known as the poset. Now take an example. We can show whether the partial ordering of the set of integers satisfying all three conditions or not. So Z be the set of all integers. What is the relation? What is the condition? The condition is greater than or equal to, is a partial ordering relation on the set of integers. So first condition, reflexive. Take one element A. A, what is the relation here? Greater than or equals to A. So A greater than or equals to A. So for any integer, so A greater than or equals to A satisfies, means so the set of integers satisfies the relation, the order pair is satisfying the reflexive. Similarly, A greater than or equals to B and B greater than or equals to A. So if A is greater than or equals to B and B is greater than or equals to A, then clearly A is equals to B. So therefore the relation greater than or equals to is antisymmetric. So satisfying this one is satisfying the antisymmetric. So coming to the transitive, what is transitive? So A greater than or equals to B, B greater than or equals to C, then automatically A is also greater than or equals to C. Therefore the relation is greater than or equals to, the relation greater than or equals to is a transitive, means the set of integers under the relation. What is the relation here? The relation is greater than or equals to, satisfying all the three conditions. What are the three conditions? Reflexive, antisymmetric, as well as transitive. So if it satisfies all these three, then we say that this is a partial ordering. So P, the set of all integers greater than or equals to, under the operation greater than or equals to, satisfying all the three conditions. Therefore, the set of integers is a poset. Set of integers is poset. Z greater than or equals is a poset. Poset means it is a partial ordering. Similarly, you can take any set, any operation, any set. So you have to prove the reflexive, antisymmetric, as well as transitive, right? One more example here we'll discuss. Show that the subset are equal is a partial ordering on the power set of set S. So already we know what is a subset. So here the operation is subset under the set. What is the set? Power set of a set S. What do you mean by power set? What do you mean by power set? The set of all subsets is nothing but a power set, right? So if you take A is an element of S. A is an element of S. So A itself is a subset of A. So A itself is a subset of A for all A. For all A. So therefore A is a reflexive. The set is satisfying the reflexive property under the operation subset are equals to. Similarly, A is subset of B and B is subset of A. Therefore A is equals to B. So the operation subset are equal is antisymmetric. Similarly, A is subset of B and B is subset of C. Therefore, A is equals to A is subset of C. So subset is a subset or equals is also transitive. So the power set is satisfying all the three conditions. What is the conditions? Conditions of poset, reflexive, antisymmetric, transitive. Under the operation, subset are equals to. Therefore, it is a partial ordering on the power set yes. Partial ordering on the power set yes. So similarly, you can go for any problem, any problem. Show that the divisibility, the relation is the divisibility, is a partial ordering on the set of positive integers. So set of positive integers, check whether the divisibility is satisfying all the three, reflexive, antisymmetric as well as the transitive. So if it satisfies all these three, then we say the set of positive integers is a poset. So A is an element of Z plus. Reflexive, A divides A divides A. So Z plus is satisfying the reflexive, right? Similarly, A divides B and B divides A. Therefore, A is equals to B. So division is antisymmetric on Z plus positive integers. So A divides B, B divides C. Then obviously A divides C. So division is transitive under Z plus. So Z plus is satisfying all the three conditions: reflexive, antisymmetric, transitive under the operation division. Therefore, Z plus and division is partial ordering on Z plus. So Z plus is the division operation is a poset. So on the set of all integers, the above relation is not partial order as a and minus a both divides each other. But a is equals to minus a is not an antisymmetric. Is not an antisymmetric. Okay. So here you are taking Z plus. So that we are getting. So if you take Z, it is not a poset. It is not a poset. So you can go for number of examples like that one. Haas diagram. What do you mean by Haas diagram? What are the conditions for the Haas diagram? So Haas diagram, a partial order less than or equals to on a set P can be represented by means of a diagram known as Haas diagram. In such diagram, each element is represented by a small circle or dot. Each element is represented by a small circle or dot. The circle for x belongs to P is drawn below the circle for y belongs to P and if x is less than y. So for x belongs to P is drawn below the circle for y belongs to P if x less than y and a line is drawn between x and y if y covers x. So x less than y, but y does not cover x, then x and y are not connected directly by a single line. So right. So simple example here. Uh, P 1, 2, 3, 4, 5 and less than or equals to be a relation, less than or equals to be a relation, then the Haas diagram. So every element is represented by circle, right? Circle. And 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 is less than 5. And so there is a relation. What is that relation? Less than 1 less than 2, 2 less than 3, 3 less than 4, 4 less than 5. Similarly, 1 is less than 5, 2 is less than 5, 3 is less than 5, 4 is less than 5. So it is totally an ordered set. So coming to the second one, right? X is equals to 2, 3, 6, 12, 24, 36. And the relation is less than or equals to be such that X divides Y. X divides Y. Draw the Haas diagram of X less than or equals and the solution of this one, right? First you have to take 2 2 a circle 2 next element 3. Is there any relation between 2 and 3? Then 2 does not divide 2 less than 3. Okay, 2 less than 3, but the condition is not satisfying. What is the condition? 2 divides 3, 2 does not divide 3, so separated, they are not connected. 2 and 3. What is the next element? 6 6. 2 divides 6, 3 divides 6 and 2 less than 6, 3 less than 6. So there is a connection. So there is a connection. 2 6, right? Next element is 12. So 12 less than 6, so that 12 here it is. So 6 divides 12, 2 divides 12, 6 divides 12, 3 divides 12. So 2 6 12, 3 online, 2 6 satisfying, 2 less than 12, 6 divides also 12, right? 24. So anywhere else, 24. So 24 and 24. Similarly, so is there a 24? There is no connection between 36 and 24 because 24 does not divide 36. So this is the Haas diagram. This one is the Haas diagram. Right? Thank you.